Third law. Newton's first and second laws apply to the motion of an individual object. However, all forces must be applied by something. Think about throwing a basketball, figure 5.10. You feel the ball push back against your hand as you throw it. You know you apply a force to the ball to make it move. Where does the force against your hand come from? Forces always come in matched pairs. Imagine a skateboard contest between Isaac Newton and an elephant. They can only push against each other, not against the ground. The one whose skateboard moves the fastest wins. The elephant knows he is much stronger and pushes off Newton with a huge force, thinking he will surely win. But will he? Newton flies away with a great speed, and the puzzled elephant moves backward with a much smaller speed. Newton wins, and always will win this contest against the elephant, no matter how hard the elephant pushes. Newton will always move away faster. Why? It takes force to make both Newton and the elephant move. Newton wins because force always come in pairs. Elephants push against Newton, and the action force pushes Newton away. The elephant's force against Newton creates a reaction force against the elephant. The action and reaction forces are equal in strength. Newton has much less mass, so he has much more acceleration. Third law, action and reaction. The first two laws of motion apply to individual objects. The first law says an object will remain at rest or in motion at a constant velocity unless acted upon by a net force. The second law states that acceleration equals the force on an object divided by the mass of the object. The third law of motion deals with pairs of objects. This is because all forces come in pairs. Newton's third law states that every action force creates a reaction force that is equal in strength and opposite in direction. There can never be a single force alone without its action-reaction partner. Forces only come in action-reaction pairs. In the skateboard contest, the force exerted by the elephant, action, moved Newton since it acted on Newton. The reaction force acting back on the elephant was what moved the elephant. The words action and reaction are just labels. It does not matter which force is called action and which is called reaction. You simply choose one to call the action and then the other to call the reaction. Figure 5.11. Why don't action-reaction forces cancel each other out? The reason is action and reaction forces act on different objects. For example, think again about throwing a ball. When you throw a ball, you apply the action force to the ball, creating the ball's acceleration. The reaction is the ball pushing back against your hand. The action acts on the ball, and the reaction acts on your hand. The forces do not cancel each other out because they act on different objects. You can only cancel out forces acting on the same object. Figure 5.12. Reaction forces. Think carefully about propelling a skateboard with your foot. Your foot presses backward against the ground. Figure 5.13. The force acts on the ground. However, you move, so a force must act on you too. Why do you move? What force acts on you? You move because the action force of your foot against the ground creates a reaction force of the ground against your foot. You feel the ground because you sense the reaction force pressing on your foot. The reaction force is what makes you move because it acts on you. When sorting out action and reaction forces, it is helpful to draw diagrams. Draw each object apart from the other. Represent each force as an arrow in the appropriate direction. Here are some guidelines to help you sort out action and reaction forces. Both are always there whenever any force appears. They always exert the same strength. They always act in opposite directions. They always act on different objects. Both are real forces and can cause changes in motion. Newton's third law tells us that any time two objects hit each other, they exert equal and opposite forces on each other. However, the effect of the force is not always the same. Imagine two hockey players moving at the same speed towards each other, one with twice the mass of the other. The force on each during the collision is the same strength, but they do not have the same change in motion. The person with more mass has more inertia. More force is needed to change his motion. Because of the greater inertia, the more massive skater will have a smaller change in motion during the collision. The forces on each skater are always exactly equal and opposite. The two skaters have different changes in motion because they have different amounts of inertia, not because the forces are different. The same is true of vehicles in a collision. When a large truck hits a small car, the forces are equal, figure 5.14. However, the small car experiences a much greater change in velocity much more rapidly than the big truck. Riding in a vehicle with a large mass does not guarantee passengers will be safe in a collision. Large SUVs are more likely to roll over during accidents. Auto manufacturers conduct crash tests to help them improve the design of cars. Safety features such as seatbelts, airbags, and anti-lock brakes help make cars safer. See Figure 515 here and answer these questions.